Hey guys, I'm Kylie. I hope you guys' summer's going well. Today we're going to talk about colligative properties. When reading through people's intros, I saw that a lot of people were going to the medical side of things. So today I figured I'd relate it back to mole fractions, vapor pressure, and osmotic pressure. So first we're going to start off with mole fractions. Mole fractions are pretty simple and there's two main steps, but it's pretty easy to make a math error if you're putting it into the calculator. You're going to find the moles of each substance. Typically, when you're doing this in a lab, you're going to be given grams. So you're going to do the grams of that substance divided by the molar mass, and then you're going to do the molar, and then you're going to get your moles of the substance. And then with that moles of your substance, you're going to do your moles of the substance divided by your total moles in like the solution. So we're going to put that in math terms to make it a little easier to understand. And I figured I'd relate it back to medical. So in this solution, we have 0.2 grams of salt and 14 grams of water put into the bloodstream. And what is a mole fraction? So typically you might use like a saltwater solution. Typically people have some salt in their body. Not a ton though, because that would dehydrate the body. So the first step you're going to do is you're going to find your moles of the NaCl in water. So you're going to do 0.2 grams of NaCl divided by 58.44 grams of 58.44 grams of NaCl. That 58.44 grams is your molar mass. So with that, you get 0.00342 moles of NaCl. And then with the water, you do 14 divided by 18.01528 grams of H2O. Remember, it's grams of the substance divided by the molar mass, which gets you 0.77 moles of H2O. Then after that, you're going to do your second calculation, which is the mole fractions of each compound. So you're half of the way there already. So you're going to do your moles of the NaCl divided by total moles, which gets you 0.00438 moles of NaCl, and then 0.996 grams for 996 moles for your H2O. And those are your mole fractions. So if you want to double check your work to make sure you do your math right, you can figure out if it equals 1. If it does not equal 1, go back and check your work. And if you have any questions, ask the teacher or Google it, because it always should equal 1. If it doesn't equal 1, go back and check your work and make sure you didn't maybe calculate the molar mass wrong or didn't type it in the calculator accidentally. So second, we're going to the vapor pressure. So vapor pressure affects how much like water can evaporate out of your skin, and that can be affected by like non-volatile solutions and solutes. Like if you had water and oil wouldn't let the water evaporate because how thick the oil is, and there's a clear line. Another thing would be like from the salt and water solution. So from the previous numbers we had 0.00342 moles of salt, and the mole fraction we found was 0.00438 moles of salt to water. And the pressure in our body is around 100 mmHg, which I calculated to be 0.132 ATMs, which is pretty small, which is right because we're inside the body. We don't want high pressure because we don't need the blood cells bursting. And then like the temperature is around 98.8 Kelvin, which temperature in the body should be around like 97.9 to 99 or 98. So that's pretty like average temperature. And then we're going to find the change in the vapor pressure. We're using Raoult's law. So since we have to find a change in the vapor pressure, a lot of the water cannot evaporate, which is not good, which is okay in a sense, but it's not 100% good because those water molecules cannot evaporate up, which makes it have a lower water pressure because how high the concentration is. So we're going to find using Raoult's law that states that change in pressure equals a mole fraction times the pressure. So in the previous step, we found that the mole fraction of the salt was 0.00438. Then we're going to times it by the pressure in the body, which is 0.132 ATM, giving us our the change in the pressure, which equals 5.78 times 10 to the negative 4 for the change in the pressure in the body for if we were to add like a salt water combination to it. And then with that, we gotta be careful because we don't want too much of a change in pressure, because if you have too much change in pressure, things could burst like red blood cells, and you gotta have like a barrier. There's a barrier. And osmotic pressure can really affect that. The osmotic pressure affects how much like the water, the barrier for how much a solvent can like flow into the permeable membrane. And our solvent in this case is the water. And so with that, we can measure how much like the osmotic pressure needs to maintain, because we don't want it going over a certain threshold, or we'll have like a solvent going into areas that it shouldn't be going into due to the force. With that, osmotic pressure we can calculate by using molarity, the universal gas constant, and temperature, which two of those constants were already given. So the only thing we need to find is molarity. With that, the molarity can be found by using moles over liters. And we know that density equals milliliters over, or density equals grams over milliliters. So we can convert the 14 grams of water that we found in the earlier step into 14 milliliters of water. But for molarity, you gotta use liters. So we had to do 14 divided by 1,000, which has 0.0014. So we're able to do 0.00438 moles of water divided by 0.00438 moles of salt. This should be salt, sorry guys. And that should be divided by 0.0014 liters of water, which has 3.13 molarity. So then we can calculate the rest of it. The osmotic pressure was 3.31 molarity times the universal gas constant 0.08206 times 98.8 Kelvin, which has to 25.4 for our osmotic pressure. Now you can check this step if all your units cancel out. That is very important. And remember, this pressure cannot go too high, because if it goes too high, that means things in the body will burst that shouldn't be bursting. And red blood cells are really important because you have to maintain those ratios. Now, if you guys have any questions, please ask them below, and I hope you guys are having a great summer.